Critical enough mass. We're very fortunate today to welcome our colleague, Dr. Michael Endl from the University of Texas, who I guess you should not start off doing planetary research, doing boring things like studying the atmospheres of stars. Sorry, did I qualify that as being boring?
Oh, pretty much.
Migrated naturally into, you were probably the first group of people who began looking for exosolar planets and characterizing them.
Not really the first ones.
Well, not the first, but the early 2000s, I guess we've gotten involved in it pretty quickly.
Yeah, I got involved in during my PhD, so in '97.
Yeah, okay.
So 20 years.
All right, that alone is depressing. But nevertheless, he's been at the University of Texas now for more than a decade, for 15 years or so now, spending a lot of time characterizing exosolar planets and searching for them. And he was involved in the recent discovery of the exosolar planet around Proxima B, which I'm sure you'll be telling us about. So, without further ado, take it away.
Thank you. So, thank you very much for showing up to my talk. Thank you very much, Casey and Texas A&M, for inviting me to give this talk. It's my first time here. It's really a very nice building that you guys have up here. I mean, much nicer than my offices at UT. Yeah, definitely. I wonder if you should dim maybe a little bit the lights.
You know what you do is I'll pull this curtain out.
Ah, okay.
The lights a little bit.
So, like Casey said, yeah, I've been involved in the field of exoplanets since basically 20 years since I started working on my PhD as a student at the European Southern Observatory. But in 2001, I moved to Texas, and I'm since then involved in the McDonald Observatory Planet Search Program. And what I want to do today is tell you the story or the tales of two worlds where I was lucky enough to got involved in the discovery of these two planets. One is Kepler 452b, which you see a very nice high-resolution image here, which of course are all artist impressions, and Proxima B that made some headlines last year in summertime. I mean, this week alone was, well, wait, today is Monday, so last week was an awesome week for exoplanets. You probably heard about the TRAPPIST-1 discovery, and there's probably more coming, I can tell you. Those 7 planets were discovered by, well, 2 were known already from ground-based surveys, and 5 more were identified by a very intensive 20-day campaign using Spitzer. And now, I can tell you, we have actually over 80 days of continued monitoring of TRAPPIST-1 with Kepler. So this hasn't been, the data just came down, and maybe, I know, another 7 planets show up or something. So very, very interesting. But let me start with a little bit of a historic perspective. It's really amazing what happened in the just past 2 decades. Basically in that time, when I got involved in this field, the very first exoplanets, but just a handful, have been detected. So first in 92, of course, came around the pulsar planets, which were really weird planets, but they were already very low mass planets and small planets. And at that time, we should have probably already had the indication that planet formation seems to be actually a very robust physical process. Because if you can form small or planets at all around in an accretion disk around a pulsar, then it seems to be a pretty stable process. And we should have maybe expected more planets. But remember, at that time, nobody had found any other planet around, especially around a normal solar type star. It just took a few more years when Michel Mayor and Didier Queloz announced 51 Peg, which was also a big discovery because it was a hot Jupiter, a Jupiter type, Jupiter mass planet in a crazy orbital period of 4.2 days. Just 2 years later, actually, McDonald Observatory published the first exoplanet 16 Cygni B, which was the prototypical exoplanet discovered by radial velocities. So what you see here with the pulsar planets, these are actually changes in the arrival times of the 1,000 pulses that the millisecond pulsar gives you. While you see here these data points here phased, here's the time series. are the radial velocity, the precise radial velocity measurements of the star. Yes?
The pulsar planet, what's the origin of that? Was that planted before or after?
No. Yeah, so good question. There cannot be planets that have survived the red giant phase and then the supernova explosion of the host star, because they're so tightly, so close to the neutron star that they would have been inside the star for most of the time. And so we think they're second generation planets. And that's why I said we should have already maybe guessed that planet formation in any type of disk around the star is a process that readily happens if you have just a disk apparently, because that pulsar sped up to accretion of extra material later on to become a millisecond pulsar, and probably those planets formed in that disk. And 16 Cygni B was just an indication of how crazy it can be, because you see the sawtooth kind of pattern of the radial velocities, which is an indication that the planet is on a very highly eccentric orbit, unlike any major planet in our solar system. But this is kind of how this whole thing started, and for many years we had maybe a few exoplanets, maybe 10, a dozen. And we are now in 2017, and the field looks like this. What you see here is orbital period on the x-axis, on the y-axis now, the planetary radius. And for many of the blue points here, these are actually the radial velocity detected exoplanets. We kind of estimated the radius from their minimum mass. But you see that the plot, of course, is dominated by the huge sample by more than 3,000 planet candidates that we got from NASA's Kepler mission. So Kepler was really a big, big revolution, a quantum leap in our field. And it showed us very clearly that maybe every single star in the sky, if it's dynamically possible, it has planets, at least small planets. Because 60% of the single stars in the Kepler field had small planets, and this is only to orbital periods of about right here, where the 60% estimate. This is actually a later, more recent plot. Of course, the Kepler results kind of are truncated right here, because after 4 years, the telescope suffered a malfunction, and it cannot point to the original. It can point there, but it cannot do the precise photometry in the Kepler field anymore. But NASA engineers came up with the solution to make a new mission out of the telescope, and its K2 is still ongoing.
What's the pinkish dots in the upper left?
That's ground-based transit detected exoplanet. So I should mention that Kepler works with the transit method. So it's actually staring, or it did stare at a certain field, a star field in the sky, and it's waiting for, if you're lucky enough, to look into the orbital plane of the planet, to see the planet cross in front of the star, and see a tiny dip in the light curve. The dip repeats, of course, every orbit once. But what we can now do is, we are now moving very, very steadily and almost with breathtaking speed to the a different question. Not only are there planets out there, obviously there are planets out there, but what about Earth-like planets in the habitable zone of stars? And this is kind of it's not yet the final published result that will come out of Kepler, but the current estimates of the frequency of small planets in the range from 1 to 1.6 Earth radii in the habitable zone of these type of stars, where we go in main sequence from the M dwarfs K to G types dwarfs and F types. And for a star, this slide was done for a presentation for where people were really interested to send nanoprobes to the Alpha Centauri system. So you have Alpha Cent A, which is basically the sun here, Alpha Cent B here, and Proxima down here. And you see the estimate of the frequency of these habitable zone planets is rather high even. It's 0.36. the uncertainty, of course, is relatively large still. So if you're a pessimist, it's maybe 10%. If you're an optimist, it's 50% of these stars, like the Sun, have an Earth or a planet at least of this size in the habitable zone. Interestingly, it goes down for the K dwarfs, for which we have better statistics because the periods get shorter, the planet becomes bigger in comparison to the star, and then the M dwarfs, there's like a mixed bag because M dwarfs are fainter, so as the photon statistics are getting poorer, but still it's easier to detect a planet of a given size because the star gets smaller. So today I want to focus on two cases of planets in the habitable zone of stars. One is around the G-type star, and the other one is Proxima B around Proxima Centauri. I kind of tell you now the story how these planets were found. And it's also a nice contrast, I think, because they were found by really different technologies, so to say, and methods. One is basically the result coming out of the Kepler mission, except those statistics that are very important. And the other one is where Proxima B was more or less discovered by traditional methods, by ground-based radio velocities. So let me first talk about the Kepler planet, Kepler 452b, which was we announced more than 1.5 years ago. And it was very special for us at this point because it was exactly that kind of Earth analog that we were looking for, that Kepler's prime science goal always was, to determine how frequent these Earth-size planets in the habitable zone of Sun-like stars are. And it was a large paper, and okay, so this, I screwed up this slide because I wanted to highlight the people that work I will now describe, and they're actually further up. Never shift something around and don't check your color box and stuff. Okay, so what happened? Well, first of all, Kepler is an interesting mission in the sense that although it's staring continuously, or it's stared continuously at a certain search field with 160,000 target stars, it had to rotate every quarter year, meaning that the star field rotates on your detected array, meaning that every star, every quarter year, goes onto a different detector with different sensitivities and characteristics. So the light curve of each star is kind of chopped up into different quarters, and they all look different. And it took some time for the people at in the science office to actually develop a pipeline that can correct for these differences and finally put all those 4 years of data together. And once they did that, they found for the first time those long period planets that you couldn't find just in 1 or 2 or 3 quarters alone. And that's what happened to Kepler 452. Here on the top you see the Kepler light curve now detrended, so the raw light curve looks much messier. And this is relative flux in parts per million, so it's exquisite photometry. Those red dashed lines are those different quarters where the spacecraft moved and rotated. There are some data gaps here. And then, if you can't see that on this diagram, everywhere where you see a triangle, the detection software had picked up a transit. So we were lucky that in these 4 years we found 4 transits of a planet, and here is the data folded to the transit ephemeris. You have a nice shallow transit here, and all the diagnostics like odd and even diagnostics that would maybe indicate a false positive, or the photometric centroid shift that would also indicate maybe a background eclipsing binary polluting your light curve and causing this dip to, turn out, well, green flag. But at this point, nobody knew. We only knew it's maybe a solar type star. It looks like a G-dwarf, but we have to characterize the star much better to really, see what the planet is. Yes.
So this that figure there showing
The odd and even?
Yeah, the odd
Yeah.
and even. Is that just the beam? I mean, how did you do the test?
Yeah, so the real, how do you do that test is that you have, you look at one transit and then you look at the next transit. And if there is any difference between those two transits, then you're looking not at the same object. And if you have an eclipsing binary system that influences your light curve aperture, so it's mixed up in the light of your target star. But what happens is, since it's not directly in your target, is that whenever you're having changes in these roles, this eclipsing binary would affect your light curve in a slightly different way that would show up as differences in the transit depths. So that it's what we look at is the depth of this transit, which is that red line here. If they don't line up for every single one of these transits, then there's an alarm going off that this is a possible false positive.
So the tester here is for transients, so it always line up to the same.
A planetary transit has to line up because it's always the same object, always the same star. So what happens next is that we got into the action basically. So the light curve detection was in May 2014, and one of the big features of or big contributions of our group was that we used the McDonald Observatory 2.7 to take high-resolution spectra of the target star to identify and to characterize that star much better. And we did that within the same month. We took the very first spectrum of the host star of this system. But we are not alone in the Kepler mission. But here I show you first the spectrum. So what you see here are, let's see, 12 individual orders, spectral orders from the tau spectrograph. The data is actually the blue in the background, and the green is a model fit that I used to determine the stellar parameters. So which one of the model libraries that we used, which star fits the data best. And these are the parameters, which is 5,650 Kelvin for effective temperature. These are the errors. This is the metallicity, so significantly metal rich, log G, surface gravity, and rotation. The thing is, it's a faint star to do this. So it's a 13th magnitude star, 13.4, almost half 13.5. So these things were typically very difficult to characterize stars to very high precision, and we are really trying to do a good job, and this was one of my contributions to develop this tool to do this for high resolution spectra, but relatively low signal to noise. The signal to noise was just 30 of the spectrum. But we are not the only ones in participating in the Kepler mission. So also, because it was such an interesting target, the other groups jumped on it as well. So we had the Harvard group using the Whipple 1.5 and the TRES spectrograph taking spectra. We had the California group hitting it with KEGG. So we kind of had 3 different sets of spectra from 3 different spectrographs. And each group was given the task, of course, and they did it anyway, even without being told, to analyze their spectra, of course, and to send in their best results. So we had different people, different instruments, different analysis tools. So I called this situation the Battle of Spectroscopy, because what would you expect if that happens in science? You would expect 3 completely different results. And to everybody's surprise, that was not the case. So here's a plot of how this Battle of Spectroscopy then actually was a very peaceful thing, because we had here effective temperature versus log G, or metallicity versus surface temperature. The blue circle is the sun, and the green is my result. The red is the result from it's actually the KEGG data that we also analyzed with different softwares, and the Whipple Observatory, let's see, I think is SPC, might be this point, just, yeah. So you see, I did. Oh, I think I used the battery.
I'm not worried about that.
So you see that my effective temperature was not really a good one. I was a little bit too cool to the rest, which clustered very nicely. And in the other case of the surface of the metallicity, I was just spot on. And this is very important to do for the host star, because in transit searches, what you really need to know is how big is your star. Because how big your star is determines how big the planet is. Because what you actually measured in a transit light curve is not how big the planet is. You get the luminosity difference as the difference in surface area. So if you have a huge star, then even a relatively large object can produce a shallow transit. Thank you. And then I got another spectrum a little bit later. And this one I show you, I'd like to show you more because it really fits into all the other results. And more importantly, I measured for both of these spectra also the radial velocity, and there is no indication that there is any change in the radial velocity. So it seems to be, a very nice single star that's not having any stellar companion. And once you have these spectroscopic stellar parameters, you can now start comparing it to model isochrones, and that was done. And in a sophisticated Monte Carlo Markov chain computation, you see the posterior distributions of stellar parameters like density, radius, effective temperature. But this plot shows it kind of nicer where Kepler, the host star, was located at. It's a little bit bigger than the sun and just a little bit brighter. And one of the interesting things that, of course, with large uncertainty that comes out of these comparison with these isochrones is that you get an age estimate. And the age estimate is about 6 gigayears, but for large uncertainty of 2 gigayears. I get back to that. Why is that interesting? So once you have those stellar parameters, now you can finally calculate your planetary parameters. And that led to a radius of about 1.6 Earth radii. And the orbital semi-major axis was basically determined now also from having the mass of the parent star. Equilibrium temperature of 265 Kelvin, very nice. Not equilibrium temperature, it's just a basic equilibrium radiative temperature. It doesn't include any atmospheric effects, of course. So our Earth without our atmosphere would also not be having liquid water on it. But the star is actually brighter than the sun, and it's the insolation of the planet compared to Earth is about 10% higher. Coming back to the age effect, it looks like we are looking at basically a very nice analog of the Sun-Earth system, just with a little bit of a bigger planet. But if that star is 6 gigayears, like the best fit shows us, then what happened was that this is kind of a glimpse into the future of our own solar system. You all know that the habitable zone, or where the Earth is, that's not going to stay, and it's not going to end for the Earth when the sun evolves into a red giant. That goes down the drain much earlier because the sun is gradually becoming brighter on the main sequence, and that star is doing that as well. So what we included in our paper was this plot where you see basically if the star is really at 6 gigayears, here's the location of the age, then it seemed like that the planet was in the most conservative estimate of the habitable zone for about 5 gigayears. And now in the past gigayear, it got a little bit too warm because the star itself is getting a little bit brighter. So this is still, up to today, the closest analog we have to the Earth-Sun pair. We think it is something like the solar system or the Earth and the Sun in the future. but that was maybe why it was so interesting, and we were so excited to announce this.
Are there other planets, like our own solar system, around this star?
No, no. There are probably other planets, but we don't know of any. So there are no other transiting planets.
Okay.
And it's fascinating, the question is that in the Kepler data, they estimated how much the mutual inclination of the orbital planes have to be. So that, for instance, if there's a Venus, if there's a Mercury, it just has to be a little bit over 10 degrees and you wouldn't see them transiting. So they can't be there.
10 degrees is
They're
a lot
just,
still, right?
yeah.
Yeah.
Maybe it was even less than 10 degrees.
Maybe
It was a few degrees, less than 10, I think less than 10.
And is there a
But-
upper limit then on what the size of a planet at the location of Venus would be? And then the sun is, would you see Mercury, for example?
Now Mercury, no, Mercury is very tough, but Venus you would see.
Venus.
Yeah, definitely. So that's, yeah.
To plug this against the flux, so what is for the star, isn't the temperature or the rising temperature or something?
Well, the temperature
Do you
changes
agree?
very little on the main sequence. The thing is the restructuring of the core. Once the star burns hydrogen into helium on the main sequence, the core changes structure and it produces more and more helium, and the particle density goes down, which compresses the core and increases the temperature and fusion rate slowly, even on the main sequence. So there's simply more coming out over time, and our sun is doing this. It was 70% 4 giga-years ago of its today's luminosity. So that this is nothing abnormal to this star. That's something completely normal that happens to main sequence stars. So let me tell you the second tale that was just announced last August. I was more or less, again by coincidence, involved in Proxima Centauri B, the discovery as well, which made a big splash. I couldn't believe actually how many journalists contacted me last August, and it lasted quite a few months. I mean, we did get the Nature cover, which was really neat, and the Nature cover showed already like the most optimistic thing, of course, that we have found an Earth-like planet with liquid surface water on its surface, but we have not. I will tell you exactly what we have found. But the excitement, not only for the public, but more for the astronomers, was that it has the potential to be something like this. And because it's around Proxima Centauri, we will be able to answer the question whether it looks like this or not in the foreseeable future. That's the excitement for astronomers. So to give you just a little bit to set the stage where we are now. We have moved, basically Kepler 452 was something like this, Alpha Centauri A. Here's our sun. Here's Alpha Centauri B. I'm not talking about Proxima Centauri, which is the M star in that system. Very, very different to the sun. Almost nearly half the surface temperature. Metallicity seems to be consistent with the much better determined metallicities of these two stars. And very important, its mass is just about 12% mass of the sun. Its luminosity, here's the luminosity, just above, a little bit over 1/1000th of the luminosity of the sun. So it's a very, very faint star. It's 11th magnitude. You can't see it with your naked eye, despite being the closest star to us. So how did I get involved? Well, like I told you at the beginning, I did my PhD at the European Southern Observatory. And right at the end of my PhD thesis, ESO built the BLT on Cerro Paranal, which are 4 8-meter class telescopes, and one of them had a spectrograph called UVES that allows this high precision radio velocity measurements as well. So my thesis advisor, Martin Purster, and I, we were sitting down and we were bouncing ideas off each other what we can use the VLT for. And then we finally ended at a very obvious observing program to look at these M stars, in particular at the nearest ones, like Proxima, like Barnard star, because they're so intrinsically faint in the optical that we did observe them, but we knew that the data was really, really poor because of the photon statistics. But with an 8 meter class telescope, you get the light into a high resolution spectrograph. And we actually observed Proxima for over 7 years, and here are the data. We had a total scatter of about 3 meters a second, which was awesome at that point of time. Nowadays, it's no longer state of the art. But you can also see that there's really nothing showing up. It seems you can fit a straight, except this point here, a straight line through it without much troubles. And this was actually what we concluded as well. We didn't see a very strong convincing signal in our US measurements. But I did determine back then, we published our data in 2008 and moved on to other things. We did determine, what can we now exclude from using these really high quality data. And if you just look at the red line here, where we have versus orbital period and mass, or minimum mass of the planet, I estimated what we should have been already seen around Proxima. And the green shaded area is kind of the habitable zone. As you see, it's very, very short periods because the star is so faint. So in the habitable zone, we got down already to about 2 to 3 Earth masses, minimum mass, in the habitable zone. So we were very happy about this. But nowadays, in hindsight, of course, 2020, I draw a line here at 1.3 Earth masses, which turned out to be Proxima B, which was just a little bit below our sensitivity at that time. So what happened next? Well, what happened next was that we ended our US program, not only because we had 7 years of data on many of these M dwarfs and didn't see many convincing signals, we saw a few and published those, but nothing around Proxima. But what also happened was that at this time, the HARP spectrographer, the ESO 3.6 meter telescope became available. And the HARP spectrograph was specifically designed to do these precision radio velocities. And the Geneva group, which was building the instrument, they had Proxima Centauri on a guaranteed time sample. So nobody else could actually observe the star for the purpose of planet searching. So we just basically published our data and moved on. But what then happened was that the Geneva group observed it for another 7 years, and they didn't see anything convincing showing up. And what then finally Guillaume Anglada-Escudé and his friend, the mathematician Mikko Tuomi, did was to just take both data sets, combine them, and they saw an interesting peak showing up at 11.2 days. So this is the periodogram where you have orbital period versus likelihood statistics of signals that they find when you combine the UVAS and the HARPS data. And as you can see, this is a moderate peak. The horizontal lines here are false alarm probabilities of, I think, 10, 5, and 1%, if I'm correct. We'll see in the next plot. So this is still not convincing enough to claim a planet detection. So what Guillaume and his colleagues then did was to do the right thing in science. When you suspect there's something really, really interesting going on, what do? You design an experiment that very quickly, and that's the big advantage of M dwarfs, the habitable zone periods are so short. You design an experiment that very quickly, very efficiently falsifies or confirms, in the best case, your candidate signal. And that came to be known as the pale red dot campaign, where we convinced ESO to give us basically the opportunity, whenever they open up the 3.6 meter telescope in the beginning of 2016, every night they do this, we want one spectrum, one radio velocity measurement of Proxima Centauri. Because if you do it with that high intensive cadence, then it should come out very, very clearly. And surprisingly, over the first 16 nights, 56 clear nights were there, so we could get data on 56 nights. So this was also with HARPS. So if you look at all the radio velocity data of Proxima Centauri, you have our old UBIS data back here in blue, the kind of standard, and you see the different sampling too. This is kind of comparable sampling, traditional PlanetSearch sampling of the HARPS observations in between, and then the pale red dot campaign, which was just 60 nights, over 60 nights. And if you do this, and you look now at the parallelogram of just the pale red dot campaign alone, you have a strong peak at 11.2 days. And what really convinced everybody of this large team that we did indeed find a planetary signal was that if you combine everything, you get a very, very strong peak. The power, the significance of this signal is even, strengthened even further, which means it's present in all the individual data sets. And that's very important because M dwarfs we know nowadays are very messy. My former graduate student Paul Robertson showed in a science paper just a few years ago that the habitable zone planets that we thought are orbiting in around Gliese 581 are just due to activity. There are no planets at all. We were fooled by the activity of the host star, which is also an M dwarf. So we have to be very careful with these things, and one of the features of a planetary signal in radio velocities, of course, is that it stays constant in period, phase, that's also important in phase, and in amplitude. So this is what we see here. But that was not all of it. We looked very carefully at the activity of Proxima Centauri. We know that Proxima Centauri is magnetically relatively active. It's a known flare star. We did simultaneous photometry of Proxima Centauri. It was known before this simultaneous photometry to be a flaring star, but within this simultaneous photometry, we saw like every other few days a flare going off on Proxima Centauri. And flares you can easily see, for instance, in H-alpha emission of the chromospheric emission. And here what I show you here is a comparison of the emission that we see in H-alpha. And we basically can take every single spectrum that we took over these 17 years or 16 years and determine, how much was the chromospheric emission level of this at this particular time when we took the radio velocity measurement. And if you see any correlation, even a slight indication of a correlation, then you're in trouble. And we fortunately didn't see anything for any of these data sets at the planetary period, which is this green line here. The rotation period, by the way, yeah?
Proxima Centauri has a proper motion of about 4 arc seconds a year. So over 17 years, it's moved about an arc minute. And the field is very, very rich in stars. Does that make for any problems?
You mean
things that it comes close to that your software may not realize?
You mean by contamination, by background
Yeah.
light?
Yeah.
You're doing high resolution spectroscopy, so you're putting the star on the slit, or in the case of HARPS on the fiber entrance. I think the fiber of HARPS is not more than 2 arc seconds.
All of your photometry was PSF?
All of the photometry.
Is all PSF photometry?
The photometry was, I assume so. I'm not sure about that. I wasn't involved.
Because you have a really crowded field and you do aperture photometry, you can get fooled.
There was the 1 meter LCOGT telescopes, and then another one in Chile, which I think was a little bit smaller.
But you wouldn't expect any periodicity.
What's that?
You wouldn't expect any
No,
periodicity from that.
no.
Right.
That
Just
would be
nature.
No, but
okay.
but one time I was observing Las Campanas and I said, taken the image with Proxima Centauri, and it was hard to find because
Yeah.
of its large proper motion, and there's so many other things, like, okay, which one is it, you know?
Yeah, we don't think we got any troubles because of this, and at least to the precision we can see. We see clearly the activity we see the rotation period of Proxima Centauri showing up in there. So if I would have anticipated your question, I would have put the plot of the photometry in my talk, but I can show you afterwards. Because you also see very nicely all these flares
I'm
going
willing
on.
to accept your assertion all as well.
So what we found now was a planet by a different method, by radio velocities. When you do this, what you get is a minimum mass of the planetary companion. So in this case, we knew the star quite well. And the amplitude, by the way, here, this is just the Harps data over the pale red dot campaign. So these are the 56 data points over 60 nights. And the blue line here is the 11.2 wiggle due to a very low amplitude, 1.4 meters a second amplitude. Keplerian signal, which translates to about a 1.3 Earth mass, minimum mass. You have a 90% probability, assuming random orientations of orbit, that this thing is below 3 Earth masses. So we're dealing potentially with a super Earth or a relatively Earth-like planet. Its transit probability is relatively low. People looked for it. People used the most space telescope to look for transits of Proxima B, but couldn't find any. It's an interesting paper that David Kipping published, because they actually saw transit-like features, but they did a very sophisticated analysis and think that these were actually not real transits that they found. And here's the radio velocity data just phased to the orbital period. It looks massive, but that's just because it's a very low amplitude signal. The amplitude, 1.4 meters a second, is just a little bit higher than our measurement precision. So what can we do with this world now? I already mentioned that astronomers are so excited about it because it's the nearest star to the sun. We're just talking a little bit over 1 parsec. So one thing we can do, hopefully in the future, when we have the GOT, or the Europeans will have the EELTs, that you have such spatial resolution that it should be no problem to directly image the planet. And Ignaz Snell has pioneered these methods to combine a very, very high spatial resolution with very high spectral resolution, where you can discern the light of the planet. In this case, it would be the reflected light from the star that is Doppler shifted by the orbital velocity of the planet and ends up in velocity space at a significantly different place. And by doing this, and he published a kind of a simulation in 2015, so before our detection, of a hypothetical habitable zone planet around Proxima Centauri, and he's almost a Nostradamus in this case, because these things, the effective temperature, the separation of 25 milliarc second is almost really identical to the real thing. Partly due to the fact that the habitable zone is very small around Proxima Centauri. So if you want to put an Earth in there, you're not far off from what we found. He of course had to assume a radius and a certain albedo. So a radius of 1.5 Earth might be, of course, actually within the realms of possibilities. And this is it actually, of the removal of the starlight. The star is over here. Here's your planet. It's estimated with the EELT, you would get maybe a signal to noise of 10. So you can then actually also start taking those photons and feed them into your spectrographs. Another approach is to look at phase curves. So we know basically from physics, simple, from gravity, that this planet is tidally locked. It's too close to the star to be not tidally locked. And now the first question we would really like to answer is whether it has an atmosphere or not. because the atmosphere, of course, would be very important for any kind of habitability. And we know about the activity of Proxima, so if there is no atmosphere around anymore because it got eroded from the intensive flaring activity of the star, then of course life will have it much more difficult. And we have a chance to observe this just using phase curves and the JWST though. You need the extreme sensitivity in the infrared. The idea is very simple. You have a tidally locked planet. If you have no atmosphere, there's no heat redistribution, so you have one very hot side and then a very cold side. So the total infrared flux from the Proxima Centauri system is modulated by the phase of the planet, because sometimes you see the hot phase of the planet plus the star, and sometimes you see the star plus the cold phase of the planet. And here are the plots that this was published last year that show you how different the various flux levels are if you have a bare rock with no heat distribution, you get up a maximum effect, or a planet with about 35% heat redistribution due to a present atmosphere. Then you can use JWST to observe whether there is such a variation. If you don't see any, then we are actually in good shape. If you see a very strong variation of the infrared flux, then you probably look at the non-atmosphere of this planet.
Just out of curiosity, what is the Earth's heat redistribution? Or would it be?
It might be just 35. No, it must be more than 35%. Absolutely, because the temperature difference is freezing. So it's pretty large. Yeah. So this is maybe even a low limit that they assume gravity. I mean, and of course, all of this goes ultimately to the holy grail nowadays in exoplanet, to do something basically akin to observational astrobiology. Proxima B would be, if it has an atmosphere, maybe potentially, if the TRAPPIST system, maybe Proxima B might be the first system that we're going to use one of these gigantic telescopes or JWST, probably a combination of all of them, to search for biosignatures, to get these super low signal to noise, but still spectra of the atmosphere of the star, and look, of the planet, of course, and to look for these spectroscopic footprints of biomarkers, which, because there are various different biomarkers, and we all know that there are various different processes to create abiological processes to create some of these chemicals. But if you have several of them, like in the Earth's atmosphere, it's a combination that gives you at least a very good indication. You really might look at some biological activity. So this is kind of on the horizon. I think a lot of the excitement that the professional astronomers felt when we announced this planet was that they said, now we have a very good target to try this on maybe 2 decades or so from now. And I end with a cautionary slide about what you always have to be careful about when you talk to the press or even normal people at a party. The Earth analog term, Earth 2.0, is always very dangerous to be announced. And the only thing I don't like with this graphics is that actually not only NASA sees a grant coming when you're involved in such a discovery, but of course people like me myself. Thank you very much.
More questions, Mike?
Yeah.
There's X-ray observations with Proxima, right? Are they useful at all in terms of?
Oh yes.
X-ray classes?
Yes, absolutely. Because as it turned out that in the X-rays, Proxima Cen gives out basically the same energy flux as the sun, despite being such a small.
So they measured it, right? to measure?
Yeah. So it's the flares, the coronal X-ray flares are, as energetic as.
So that's like bad news for.
It is.
Right?
It is definitely bad news. Yeah.
So, so when you draw those gray bands of habitable zone, that doesn't.
No. So the habitable zone is very relative primitive concept. It goes back to the liquid surface water. But for instance, in the figure that I showed for Kepler 452b, this one here, the only thing that people have done by now was to include the atmosphere physics a little bit. So, for instance, the Venus this is an updated habitable zone. Koparapu has worked on this over the past few years. So the whole concept started with a paper by Jim Casting, right? Basically just using more or less just radiative processes. So this is the distance that you should have to be, that the equilibrium temperature is kind of in that range. Now this includes also like runaway greenhouse effect scenarios, and that's why Venus in the classic habitable zone, Venus is in the habitable zone, and these no longer. So that's the classic habitable zone, and this is now these conservative estimates. If the planet has an atmosphere, which it needs it for water to be on the surface stable, then you avoid runaway greenhouse effect.
A great follow-up question. So there's seems to be a lot of activity going after red dwarfs these days to find exoplanets. Is that just because it's easier for transit perspectives, certainly, but theoretically, there's no theoretical basis for this, right? It's just purely an observational thing that there's more dwarfs in the sky, and it's easier to find planets.
Well, yes, and it's also
Even though
easier.
less understood in terms of credibility, that's probably
Right. So this is a very big discussion, ongoing discussion in the field of astrobiology, because it was always traditionally, G dwarfs, sun-like stars, Earth's around, like the Kepler goal kind of. And but over time, many people have always pointed out, well, but the N dwarfs, they live longer, they're more abundant. Maybe if they have rocky planets in the habitable zone, then they would be actually dominating the kind of biomass in the universe. And there has been always like people who said, well, but they are tidally locked, so you have the atmosphere evaporating at one point and freezing out at the other, so forget it. And then 3D climate models came around and said, no, there's enough heat redistribution that these atmospheres remain stable. And then they said, well, but then you have the flares, which come with a lot of high energetic particles, which will over time erode the atmosphere. So then you need a magnetic field. So we are really going and moving into the details, and it's important for us astronomers. So it's that we want to answer exactly those questions about Proxima B. Does it have an atmosphere? Does it have a magnetic field? And so on. If we find it has an atmosphere, I bet it must have some kind of magnetic field as well. With that flaring activity of the host star, without a protective magnetic field, could probably not survive. And just to mention, it's not only transit, but the M dwarfs are such a great opportunity for my field, the radial velocities as well, because the host star mass is so much lower that we can also detect Earth-massed planets around the G-type star Kepler 452b. Even if it wouldn't be so faint, if it would be Alpha Centauri, we wouldn't be able to measure its mass with today's technology. Yeah.
So with the direct imaging that Ignace Snellen simulated, would that be good enough to get you Sinai and really nail down the mass? I mean, that
yes, absolutely. So once we get the direct detection, we will get orbital information, astrometry, and then we will have the true mass. Yes.
Is Gaia sampling enough to see the reflex motion? Spectrometrically?
No, interestingly, no, because it's so close to the star. So the star, of course, is very close, so the astrometric perturbation should be relatively large, but unfortunately, it's so nearby that it's less than what Gaia can. At least, I think that's what I asked Fritz Benedict that question, and he said no. He looked into it. It's not going to be a
Okay, let's thank Mike again.
Thank you.